Hi everyone, in this video we're going to go over the solutions for the worksheet of the week. In this week we're going mostly over solutions with things in terms of the criteria of comparison in the integral test. The question number one goes with what is the value of c so that the sum from n equals 2 to infinity of 1 plus c to the minus n is equals to 2. So we have information about what happens when we have a geometric series. And so is the series for n equals 0 to infinity of a r n, and this is a, and this is 1 minus r to the n over 1 minus r. So if it's possible that we relate this to this, then we'll be able to produce the same result. So to be able to start from 0, because notice that this is starting from n equals 0, that means a plus ar squared plus. So we want to create the same effect here, but we're starting from n equals 2, so that's not doing that. This is starting from another different point. So what we're going to do is we're going to factor out 1 plus c. So we're going to do 1 plus c squared factor out. And so now this is going to be the series from n equals 2 to infinity of 1 plus c to the minus n minus 2. And so if you think of this series now, it's like you're saying, oh, okay, so this is now 1 over 1 plus c to the n plus 2. Okay? Because this is essentially what the minus is doing. The minus is just 1 over this. So now that I have this here, then I have it in the correct way. Sorry, wait a minute. This would be n minus 2. Right? So it needs to be a plus 2 here. So if it is a plus 2, then it's a minus 2 here. Yep. So minus 2 here. Okay, so instead, so let me rewrite this whole thing here. This a here in front is this 1 plus c to the minus 2. So now according to this, I can use this geometric series. Now since we're going to assume that c is a certain value, so that produces convergency. So we need that r equals 1 plus c is less than 1. Okay, that's the first thing. That's the first assumption that we're going to have. And so in that sense, this is going to be convergent, and it's going to be convergent to 1 plus c to the minus 2, which is the a, and it's going to be convergent to times 1 over 1 minus r. But r is 1 over 1 plus c. Okay? So now this is our r, and now notice that this has to be equals to 2. So essentially we gotta solve this equation now, and this implies that 1 plus c squared times, and then let's simplify a little bit this here. This is gonna be 1 plus c minus 1. 1 plus c minus 1 over 1 plus c, but I'm gonna just put this 1 plus c at the top, and then this is gonna be equals to 2. So simplifying again, this 1 goes with this minus 1, and so this is just going to be 1 over 1 plus c, and then times c is equals to 2. Then from here, we can just find out what the value of c is. This is going to give me a quadratic formula. I'm gonna have 1 is equals to 2 C1 plus C. Okay, and then 1 is going to be 2C plus 2C squared, or 2C squared plus 2C minus 1 is equals to 0. At this point, then I need to solve this by a quadratic formula. This means that C is minus 2 plus or minus 2 squared minus 4 times 2 times minus 1, so plus, and over 2 times 2, which is 4. And so this is going to give me minus 2 plus or minus, and this is 8, and this is 4, so 12, and over 4. Now I can simplify this a little bit more. This is square root of 12 can be seen as the square root of 4 times the square root of 3, and so that will be 2 square root of 3. So I can simplify that. So this is minus 2 plus or minus 2 square root of 3 divided by 4, and so I can simplify even more, and this is minus 1 plus or minus the square root of 3 over 2. And now let's evaluate what kind of value this is. So if we pick Decimus calculator, or a calculator in general, and we're just gonna do what is minus 1 plus a square root of 3. And so this is like 0.7 and divided by 2, right? So this is 0.36. It's a very small number. And now we're gonna do minus 1 plus square root of 3, and then divided by 2. Sorry, minus here. And so this is minus 1.36. Now these are the values of C. Now if I do this as a value, notice that if I'm flipping this around, if I'm doing 1 plus C, this would be 1 plus 0.36 would be 1.36, right? But doing this to the minus 1 will be 0.735. So this is a good candidate to make convergent this series. So this one is a good value of C. Now let's see what happens with the other value of C. So if I do 1 minus 1.36 yeah, notice that when I do that, this is actually giving me minus 2.73. So with this value of C is not going to be convergent. So this is not a good value for this. So the value of C that I'm going to be able to use is actually with the positive. So it will be the minus 1 plus square root of 3 over 2, which is 0.366. With this value converges, and then I can have that this is equals to 2. Okay, so that's the result for this first series. Now let's transition to the second series. So exercise 2 is actually very similar to the exercise 1, but in here we're not looking for specific values of c, we're looking for specific values of x. But you can still consider this as something of the form r to the n. And so you know that this is going to be convergent when absolute value of r is less than 1. Because x can be positive or negative, that's why I consider more the absolute value here. Now, notice that this means that this is convergent if the absolute value of x minus 4 is less than 1. And so this is giving me an inequality by the absolute value where x minus 4 is between minus 1 and 1. And so that means that if I add 4 to everything, this is going to give me between 3 and 5. So that's the values where this series is going to be convergent. Now for exercise 3, we want to use the integral test to show that the series 1 over n log of n squared converges. And then use the third partial sum to get the upper and lower bounds for the series. So first thing is we got to consider, well, we have a function f of n equals 1 over n log of n squared. We know that this is positive. We can guarantee that this is continuous, and you can kind of say that this is going to be decreasing. And you can kind of prove this really quick by doing the derivative. F prime of this is just like essentially you have product rule of different things. You can consider this if you consider this function as 1 over n log of n to the minus 2, then that implies that f prime is going to be minus 1 over n squared times log of n to the minus 2, and then plus 1 over n, and then the derivative of this, which is going to be minus 2 log of n to the minus 3, and then by the derivative of log of n, which is 1 over n, so this is going to produce a 1 over n squared term. Now notice that the log of n is positive when n is bigger than 1. So in general it's positive. This term is positive, this term is positive, but this negative term is going to transform this into a negative function. So this implies that f is decreasing. Okay, because f prime is less than 0, then that implies f is decreasing. So this satisfies everything that we need by integral tests. And so by integral test we can check the series from 2 to infinity, and this goes to from 2 to infinity of 1 over x log of x squared dx. And now we do clearly have a substitution here. U equals log of x. The u is 1 over x dx. So you can see the 1 over x here. And then we can transform this into the integral of 1 over u squared du. Okay? And of course, then we can go back to knowing that this is going to be the limit when t goes to infinity. And this integral, by the way, this is u to the minus 2, so this is just u to the minus 1 over minus 1 when you integrate. So this is just going to be limit when t goes to infinity of log of x to the minus 1 over minus 1 between 2 and t. And so of course this is limit when t goes to infinity of minus 1 over log of t plus 1 over log of 2. And so you can see here that this goes to 0, and so the whole thing converges. The whole thing converges to 1 over log of 2, or the sum here is going to be approximately 1 over log of 2 when it goes to the infinite. Now, but this says, well, prove that this converges. So this is a good measure to prove convergency. But now we want to check with the third partial sum and to get the upper and lower bounds for when the series is converging to. So the upper and lower bound are given by, for the residuals, are given by the n plus 1 to infinity of the function. And I can also check the integral from n to infinity of the function. So these are the bounds that you're supposed to get, the upper and lower bounds here. So since we're going for the third partial sum, which by the way, this is just, since it starts from n equals 2, so x equals 2, x of 2 will be just 1 over 2 log of 2 squared, right? So s of 3 is going to be this, but also plug in on 3. So this is just the third partial sum, and you want to check how much this is going to approximate at, which you can find out what this number is, but then make sure to calculate what this residual is. And so for this bounds, I'm not going to repeat the calculations here, but since n is equals 3, then this is going to be the integral for 4 to infinity of 1 over x log of x squared. And then also the integral from 3 to infinity of 1 over x log of x squared. As you can see, since it has the same behavior that this does, when we get the integrals going to infinity, this is just going to provide you with 1 over log of 4 and 1 over log of 3. Doing exactly the same integration here. Okay, so going to produce those values. And so that's the end of question 4. Now for question 5, the last question of this worksheet, it says determine the convergence or divergence of the series. And we have the series from n equals 1 to infinity of 1 over n cubed plus 2. But now n cubed plus 2 is bigger than n cubed. So we can say that 1 over n cubed plus 2 is less than 1 over n cubed. And so by that regard, we can use the comparison test. We're going to have that 1 over n cubed plus 2 is less than 1 over n cubed. And we know that this by integral test converges. And you can say the integral from 1 to infinity of 1 over x cubed dx converges. And so by comparison here, then I have that this one converges. And so we have to use the integral test here, but we used this in the previous video, so that's why I'm not redoing the calculations. In the previous video, we actually proved that this is converging by integral test. So I'm now only going to use it by comparison, and by comparison to the other one is going to make that the big one converges. Okay, so that's the end of the worksheet for this week.